All right, folks, let's talk about thermodynamics. Previously, we've talked about enthalpy and heat in our discussions on thermochemistry. We've also introduced some of the laws of thermodynamics, but we actually haven't gone into depth into them. So today what we want to do is we want to discuss entropy, free energy, and eventually we'll get to equilibrium. So what we really want to get out of today's lecture is we want to understand this concept of spontaneity. We want to hit on the concepts of enthalpy that we've already known. So enthalpy is delta H. And then we'll also introduce this concept of entropy, which is delta S. So let's start with spontaneity. So whenever we talk about spontaneity, sometimes we have this misconception that spontaneity means that something is occurring really fast. Well, spontaneity doesn't necessarily mean that it's occurring fast, it just means that over time this will happen. So what we're going to say about spontaneity is that if a process is spontaneous, it proceeds on its own without external influence. So let's say that we have a waterfall, okay? So we have water falling down from some point up here to a point down here. So the process of water flowing from the top to the bottom of our waterfall, that is a spontaneous process. We won't see water going up the waterfall. But what will happen is for a spontaneous process, we're always going towards equilibrium. So let's go ahead and think about this in terms of if we consider we have two glass bulbs down here. Let's say that these are closed off. On this left-hand side, we'll suppose that we have a number of gas molecules present in here. So what happens whenever we open up this valve right here? Is the gas going to stay on the left-hand side? What happens if there's a different gas over here on the right-hand side? How will this gas behave? Well, we know that it's not going to stay in place. So if we were to open this up, we will see that some of the gas particles that are on this left-hand side will flow over here, and some of the gas particles over here on the right-hand side will flow over here, and some might end up staying right here in the middle. But we're going to end up with some sort of equilibrium, okay? And so that's a spontaneous process. Now, if you were to have a mixture of these gas particles, it would be a non-spontaneous process to resort them, so we end up with all of these red particles here and all of these green particles there. So that would be a non-spontaneous process. So the last thing that I do want to mention is whenever we're talking about spontaneity, we said that it doesn't necessarily mean that it's going to be going fast, but the speed of the reaction really depends on that activation energy. How much energy does it take to kind of kick this reaction into gear? And so we can end up tying this back to kinetics if we would like. So now let's go ahead and review enthalpy. So recall that enthalpy is looking at the heat flow into and out of our system. So if we have our system, we could have heat flowing inward. And if heat is flowing into our system, heat is being absorbed. So that's an endothermic process. Okay, we could also have heat leaving our system. And if heat is leaving, heat's being released, that is an exothermic process. So one of the things we do want to recall that enthalpy is the heat flow into and out of the system. So that's the heat flow at constant pressure. So we'll write delta H is equal to Q sub P. So can we predict spontaneity by enthalpy alone? Well, you're probably guessing since I'm asking that question, the answer is actually no. We need something else, and we have to introduce this concept of entropy. So entropy, we're going to look at more of a qualitative view today, but entropy is looking at molecular randomness. Well, what does that actually mean? Well, entropy is looking at the amount of disorder, okay? So we're looking at how disordered our system is. And if you would like, you're welcome to go through and read, and I'll put up a lecture later about how we're trying to maximize the translational energy level in that distribution. But what we'll find out about entropy is, of course, we would represent entropy with delta S. And then entropy is also a state function. So remember that it only depends on the present state and not on the path. So let's actually talk about some of the characteristics of entropy in states of matter. So let's go ahead and consider our three states of matter. So we know our three states of matter that we look at in this class are solid, liquid, and gas. So how do solid, liquids, and gases differ from each other? Well, we know that solids, they could have a crystal structure, and they are very well organized. Okay, so these are the most ordered. We know that for a liquid, we still have an abundance of intermolecular forces, and the molecules are able to flow by each other, but it's still relatively ordered. And then once we get into the gas phase, this is the least ordered, and it's random-like behavior. So what we can say about the entropy is the entropy of a solid is less than the entropy of a liquid, which is much less than the entropy of a gas. So the gas here is our most disordered system, and the solid is our most ordered system. So what we'll do is we start to look at the laws of thermodynamics in one of our subsequent lectures, is we will look at how we can compare the entropy of the different phases and look at a chemical reaction and determine whether the reaction itself is a spontaneous process or a non-spontaneous process.